So in this lecture, we're going to look at some applications of the counting that we've done in the previous lectures. Of course, counting is the main application of the counting that we've done in the previous lectures, but here we're going to do something a little bit different. So first, let's go back to something we talked about previously in the semester, which is cardinality. If I have a set with n elements, how many subsets does it have? So previously we said there are 2 to the n subsets. We can now frame that as one of the 4 cases of counting that we had before. So I have a set, so here just have a sample set with A1, A2, A3 up to AN, have n distinct elements here, and I want to choose a subset, any subset. Okay, so I'm going to perform n experiments. Each experiment is to either include an element in the subset or not. So I go to A1 and I decide to include it or not. And then I move to A2 and I decide to include it or not. And at the end I have some elements that I've included, possibly 0 elements that I've included, and that determines my subset. So there are 2 to the n because there are two options, 2 possible outcomes, include or don't include for the first element, 2 options for the second, 2 for the third, etc. So I have 2 to the n possible outcomes. Total number of subsets is 2 to the n. Okay? So that is order matters, because if I decide to include A1 and not A2, that's different from including A2 and not A1. I get a different subset if I do that. So the include and don't include, the order in which those outcomes appear, makes a difference in what subset I end up with. And there's no replacement, which means I'm never going to include the same element in my subset 2 times, because the thing can only be in a set once, at most once. Okay. So now we're going to look at something else called binomial theorem. Binomial theorem says that for any real numbers x and y, if I do x plus y raised to the power n, I get a sum of this form. Right? So I'm going to have x to the power r, y to the power n minus r for all these r's. I'm going to have, so for example, if I have n to the third, I'm going to have x to the third and no y term, and then an x squared y, and then an xy squared, and then a y to the third term. So those are the terms that are going to be in the expansion if I take x plus y to the third and expand it out, and they're going to have some coefficients, and the coefficients are given by our binomial coefficients, right? And this is the reason they're called binomial. Binomial theorem comes from the fact that there are 2 numbers here. Okay? So we can prove this by induction. This is actually a pretty easy thing to prove by induction. It's almost made to prove by induction, but we don't want to do it that way, because if we prove it by induction, we don't really understand where this formula came from or why it's true. We can prove that it's true without really understanding it if we have the formula. So we'd like to frame this as an experiment. In order to expand x plus y to the power n, what I've written out is x plus y n times. And now I get the actual value of this by picking, I move to the first set of parentheses and I pick either x or y out of there, and then I move to the second set of parentheses and I pick either x or y out of there, and I keep going, and every term in the fully expanded expression I get by multiplying one of the terms out of the first 2 parentheses by one of the terms out of the second 2 by one of the terms out of the third set of parentheses, etc. So now I want to know how many ways can I get, say, well, if I go through the parentheses and I pick r, or I pick x r times, then I have to choose y n minus r times. Or if I have n sets of parentheses and out of x of them I choose r, then that means I have to be choosing y, the other n minus r sets of parentheses. So how many times can I choose x r different ways? Well, it's pretty obvious, right? So we know how to do, I have n sets of parentheses and I want to draw x from r of them. There are n choose r ways for me to pick the r sets of parentheses that I'm going to pick x from. Okay, so that's the reason there are n choose r. This x to the power r, y to the power n minus r occurs n choose r times in the expansion. Okay, so another way to think about it is, so here this is n equals 0. This row is n equals 1. So I'm going to go ahead and write it down. 2, 3. So these are my n values. So x plus y to the power 0 is just 1. And then x plus y is, to the first is x plus y. X plus y to the second is x squared plus 2xy plus y squared. Right? X plus y to the third is x to the third plus 3x squared y plus 3xy squared plus y to the third. So, well, what I'm doing here is I'm making another decision tree. I start with 1, and then every time I can either multiply an expression by x or y. If I multiply by x, then I have drawn an arrow down to the left, and if I multiply by y, I draw arrow down to the right. So take 1 and multiply by x, I get x, and I can multiply that by x and get x squared, or I could multiply that by y and get xy. But if I go yx, I get another xy term, right? So multiplying by x and then y gives me an xy, and multiplying by y and then x gives me another xy. That's why there are two of them in the fully expanded expression, x squared plus 2xy plus y squared. So the terms that I get are given by this triangle and this kind of tree expansion, and it's kind of obvious where each type of term came from. Right? So I can just follow the arrows and figure out how did I get an xy squared. I get it multiplied by x and then y, or by y and then x. Now, how many times each of these expressions occurs in the expanded quantity, well, it just comes from Pascal's triangle. So here, that one is here, it just occurs one time. X and y, they occur one times. X squared, y squared, here they have the ones, they occur one time, but the 2xy, this xy is going to occur two times. Okay? This x squared y is going to occur three times. Okay? So when I expand this out, I put these coefficients on it from Pascal's triangle. So it's very easy to kind of figure out what terms should be there, and then draw the appropriate level of Pascal's triangle to figure out what my coefficients should be. Rather than actually foiling out x plus y to the third, I can make put the terms that I know have to be there, and then use Pascal's triangle to figure out what their coefficients should be. When we think about it this way, it's pretty obvious why Pascal's triangle gives me the right coefficients, is because, well, I'm going to get an x squared y term from these terms and these terms. So how many of these are there, and how many of these are there, and then when I add those together, it tells me how many of these I'm going to get. And that's exactly how we figured out Pascal's triangle, was to take the number here, and then add it to get the number here. So, and now we can put these two questions together. So binomial theorem tells me that for any real numbers x and y, x plus y to the power n equals this sum. Now we can plug in a specific value for x and y. Just plug in x equals y equals 1 on the left, I get 2 to the n. In the right, I get sum as r goes from 0 to n of n choose r. So if we recall, this, if I have a set with n elements, this is the total number of subsets. Okay? If I have a set with n elements, then this is the number of subsets that have exactly r elements in them. So if I add that up between 0 and n, I'm going to get all of the subsets. So here, this is telling me again that the total number of subsets is 2 to the n. As I can recover it from knowledge of how many subsets of size 0 and size 1 and size 2 there are. Right, so here we're counting again the total number of subsets. Right. So I want to look at another application. So let's say we have a differentiable function. So we've all taken calculus 1. We know what that means. F with a superscript r in parentheses is going to denote the rth derivative. F with a 0 here is just the function because we've taken the derivative 0 times. And we have this thing called Leibniz rule, which looks a lot like binomial theorem. If I take the product, f times g, and then take the nth derivative, I get something like this. I'm going to have f to the rth derivative and g to the n minus rth derivative, and that term is going to appear this many times in choose r. Okay? So when n equals 1, this is just the product rule. And so we can think about, so why is this true? Why, for example, would if I take the third derivative of f times g, and I think about the second derivative of f times the first derivative of g, and ask, why is this term here 2 choose 1 times? I'm sorry, 3 choose 2. Why is this term here 3 choose 2 times, which is just 3? And you can think about it as, well, I'm going to start with f and g, and then I'm going to take three derivatives, and I'm either going to take a derivative of the f term or the g term. Okay? So I can go first the f, and then the g, and then the f again, and I get an f double prime g. Right? So I started with f and g, and then I took a derivative of either the f part or the g part, and I did it 3 times. Okay, I took that derivative 3 times. Okay, f, g, f, and here I did f, f, g, and I ended up with the same end result. And here I did g, f, f, ended up with the same result. So I can take a derivative of the f term and the g term, take the derivative of the f term twice and the g term once. Each of those is going to give me an f double prime g prime, but I can do those in different orders. Okay? And in fact, I can do that in this many different orders. So if I have 3 steps, I'm going to do 3 choose 2. That gives me the total number of ways to choose which of the 3 steps I'm going to take my 2 derivatives of f on. Okay? So maybe this one is a little more helpful. Looks a lot like what we just did. So here, start with fg. I can take the derivative of the f term or the g term. Take the derivative of the f term or the g term. F term or g term. Each time, if I have f prime g and fg prime, if I start with f prime g, take the derivative of the g term, I'm going to get f prime g prime. Same thing. If I start over here, fg prime, and take the f derivative, I also get f prime g prime. So I'm going to get this term from these 2 terms. Okay, taking the g derivative of this one and the derivative of f over here. Okay. So the reason that I get 2 of these in the expansion is because I get 1 from here and 1 from here. I'm going to get 3 of these. The reason I get 3 of these is I get 1 from here and 2 from here. So it's exactly like x to the power r, y to the power n minus r, except instead of powers, it's derivatives. F to the third derivative of f, and the n minus, the rth derivative of f, and the n minus rth derivative of g. The coefficients come exactly as they did for the binomial theorem. So we also have multinomial coefficients. So binomial coefficients were, I have a set with n elements, and I want to know how many ways are there to choose a subset of size r. Okay. So we can ask, if I have a set with cardinality n, how many ways are there for me to split it up into 2 subsets, where the first one has r elements and the second one has the other n minus r elements? Okay, so instead of talking about choosing one set, I'm talking about choosing 2 sets. The answer is exactly the same. If I ask, I have a set with n elements and I'm going to choose a subset of r elements. Well, if I choose a subset of r elements, then everything I didn't choose is automatically the other set with the n minus r elements. So binomial coefficients and the n choose r is not just telling me how to choose a single subset, but telling me how to partition a set into 2 subsets, where the first subset has r elements and the other subset by default would have to have the other n minus r elements. So using that, we can ask a parallel question, but with more than 2 sets. So I have a set A with n elements, and I want to partition the subset into k. I want to partition A into k subsets, and I want A1 to have R1 many elements, and I want A2 to have R2 many elements, etc. How many ways are there to do that? Well, of course, there's a restriction, is that R1 plus R2 plus R3, etc. has to add up to n. If it's a partition, I'm taking A and splitting it up into these disjoint sets. If it's a partition, then the total number of elements among these sets has to add up to n. Okay? So here's a restriction. But assuming that our r's, so n and r are things that we choose, assuming that we satisfy the restriction, that all of our elements are accounted for exactly once, the answer is this thing that looks exactly like our binomial coefficients, but just with more numbers. N factorial over r1 factorial, r2 factorial, etc. Okay. And here we note that n minus r is n factorial over r factorial n minus r factorial by definition. Right? So n, and then down here on the second row I have a comma. Right? I get r factorial n minus r factorial in the denominator. That is n choose r by definition. So we said before, if I take my set and I choose r elements, then by default I've chosen, if I'm splitting my set A into 2 subsets, and the first one has r elements, then the other one has to have the other n minus r elements. Okay? So this result perfectly generalizes our n choose r value. Okay. So we have a little proof here. So I think I'm going to skip this page. Go to this picture. I think this picture is better. So I have a set A, and I want to pick A1, and then everything that's not an A1, I'm just going to call the rest of it. Okay. How many ways? So I have A, and I want to choose A1, and A1, I want it to have R1 elements in it. How many ways can I choose A1? There are this many ways to choose A1, and that's just the regular n choose R1. Okay. So I have a set of size A, I want to choose a subset of cardinality R1. There are this many ways to do that. Okay. And now I have the rest of it. And now from the rest of it, I want to choose A2. Okay. So now this B1 doesn't have n elements anymore because over here I took out R1 many elements. So A had n elements, A1 had R1 elements, so B1 has n minus R1 elements in it. And out of that, I'm going to choose R2 elements to be in the set A2. So how many ways are there for me to choose A2 out of what's remaining here? Well, we know that. This B1 has n minus R1 elements because I started with A and took out R1 to make A1. So B1 has n minus R1 elements. And from that, I choose A2. There n minus R1 choose R2 ways to do that, which is the number that's here. And then everything that I didn't choose is in B3. And then I want to choose A, or is in B2. And now I want to choose A3 out of that. Well, now B2 has n minus R1 minus R2 elements. So I took A, took out A1, that's minus R1, took out A2, that's minus R2. So B2 has this many elements in it, and I want to choose R3. I want to choose A3, which means choose R3 of those elements. And there are this many ways to do that. So I'm just repeatedly using the binomial coefficients that we had before and choosing one set at a time and then choosing the next set from what's left. Okay. We eventually get down to bk minus 2. Okay. In bk minus 2, I choose ak minus 1. And at this point, bk minus 2 has this many elements left. Okay. And then from those, I want to choose this many. Right. And then, then I'm going to have n minus R1 minus R2 minus R3 minus RK minus 2 minus RK minus 1. And that's just RK because the sum of the R's is n. So once I subtract everything, R1, R2, R3, RK minus 1, all that's left is RK. So when we get down here, when I choose AK minus 1, I only have RK elements left. And there's no more choosing to do. Whatever's left at this stage has to be AK. Okay. So there are this many ways to choose the A1, and then once we've done that, there are this many ways to choose the A2, and then this many ways to choose the A3, etc. And if I multiply this all out, I see that this part was in the denominator from our first choice, and it's the numerator in our second choice, so they cancel. This point is in the denominator of our second choice and the numerator of our third choice, etc. I keep going. And the n factorial is left here. R1 is left, R2, R3, RK minus 1, RK. That's all that's left. This is our multinomial coefficient. So we have another way to think about it. So I want to take A, and I know how many permutations there are of these A elements. They're n factorial permutations. Okay. So now I'd like to think, if I take A and split it up into k subsets, and then for each of the, such that the first one has R1 elements, and the second one has R2 elements, and the third one has R3, etc., then I can make a bunch of permutations that go along with this by, well, the first set has R1 many elements. There are R1 factorial many permutations of the first set. There are 2 factorial many permutations of the second set, and R3 factorial permutations of the third set, etc. And so I can do whatever permutation I want on A1, and then whatever permutation I want on A2, and then whatever I want on A3, and then concatenate them. Right, so take the elements of A1, permute those, and those are first part of my permutation, and take A2, permute those, that'll be the next part of my permutation, etc. And I don't know how many permutations can I get from taking this set of sets, permuting them, but then leaving them A1 first, A2 second, A3 third, etc. And there are r1 factorial times r2 factorial times r3 factorial, etc. many ways for me to do that. Whatever permutation I want a1 times number of permutations on a2. So here again, I've taken a and the number of permutations on a, split them up into boxes. I can count the number of things in each box. Each box contains r1 factorial, r2 factorial, up to rk factorial, many permutations. That's the number of permutations in each box. I know that altogether I have n factorial permutations, and each permutation is in one and only one box. So I can count the number of boxes by dividing, and the number of boxes is exactly the number of ways to take A and split it up into subsets, such that the first subset has R1 many elements and the second one has R2, etc. So it's another way to get these multinomial coefficients. And we also have multinomial theorem. So binomial theorem was for x plus y. It was binomial theorem because I had two things, x and y. Here, if I have k things, x1 plus x2 plus x3 up to xk to the power n, well, all of my terms over here, they're going to be x1 to a power times x2 to a power times x3 to a power, etc. The powers are going to add up to n. So the different terms that I'm going to get here are going to be all the choices of r1, r2, r3 such that they sum up to n. And if I want to know how many times, so for example, if I have x1, x2, x3, and n equals 6, then I could have an x1 squared, x2 squared, x3 squared, and I want to know how many times is that going to appear here, and it's that coefficient. For exactly the same reason, I want to write out x1 plus x2 plus x3 in parentheses 3 times. From the first set of parentheses, I choose either x1, x2, or x3. Second parentheses, I choose either x1 or x2 or x3. Third parentheses, I choose either x1 or x2 or x3. And I want to know, if I have 6 sets of parentheses, I want to know how many I have to choose a subset of them from which I'm going to choose x1. And then I'm going to pick a subset of them from which I'm going to choose x2. And then all the rest, I'm going to choose x3. How many ways are there to do that? Well, I have 6 sets of parentheses, and I'm going to choose 2 to be in my a1 subset. So of my 6 sets of parentheses, 2 of them will be the ones where I choose a1, and then x1, and then 2 of them will be where I choose x2, and then the other 2 will be where I choose x3. So it's like taking my set of 6 parentheses. Okay. Just for example, let's say I'm going to choose x1 from the first and fourth, and then I could say, well, a1 will be 1 and 4. Okay. A1 is the sets of parentheses from which I'm going to choose x1. And then let's say here I choose x2, and here I choose x2. So we get 3 and 4. A2 is 2 and 3. 3 and 4, 2 and 3. Okay. So this would be one way for me to get an x1 squared, x2 squared, x3 would be for me to choose x1 out of the first and fourth sets of parentheses, and x2 out of the second and third, and then obviously x3 out of the remaining 2. And so this is, I can think about this as, okay, the parentheses from which I'm choosing x1, that corresponds to my a1 set. The parentheses from which I'm choosing x2 corresponds to my a2 set, and then a3 is everything else. And then you can see here how you can identify choosing x1 2 times and x2 2 times and x3 2 times with the number of ways to take this set of 6 and split it up into 3 subsets such that each subset has 2 elements. Each subset corresponds to the set of parentheses from which I'm choosing either x1 or x2 or x3. And that is the reason that this multinomial coefficient appears in front of this term. And again, this sum is going to go over all of these sets of indices, r1, r2, r3, up to rk, which add up to n. These are non-negative integers. We also have the similar Leibniz rule. If I want to have f1 times f2 times f3 up to fk, and I want to take the nth derivative, it's going to be exactly like this. It looks exactly like this, except these are not raising to power. These are taking derivatives. Other than that, everything else is the same.